Okay, let's have a think about Friedel crafts. I love Friedel crafts. I've got no idea why. I think because it was just so when I did my A-levels, and then when I went to university, I actually tried to understand it and it made a lot more sense. And I realized how useful it is in synthesis of drugs and chemicals and stuff. But it is really cool, Friedel crafts. So Friedel crafts, you can have acylation and alkylation. Not all examples do both. We're only looking at acylation here because that is across both, across all the examples, sorry. So Friedel crafts acylation feels like a very, very scary mechanism, but it's not. It's identical to nitration. It's identical to halogenation. It's the same. It's just the electrophile has changed, and the electrophile just looks a little bit more scary. That's all. So how do we create the electrophile, and what is the electrophile then? We would normally start with an acyl chloride. Acyl chlorides, the name of the acyl chloride, that's telling us the functional group. The functional group is carbon double bonded to oxygen, singly bonded to chlorine, acyl chloride. The acyl tells me that it is a carbon-based double bond to oxygen group, chloride with a chlorine on it. Makes sense. Why do we need AlCl3 to create our electrophile? What is AlCl3's purpose? That is what's called a halogen carrier. It is there to create the electrophile. You need a halogen carrier, so you can use AlCl3 or you can use FeCl3. Just use whichever halogen. So if we've got acyl chloride, we would use AlCl3. If you've got an acyl bromide, for example, you'd use AlBr3. Makes sense, hopefully. Your halogen carrier needs to have the same halogen as your acyl chloride, as your acyl halogen, acyl halide. The halogen carrier is there, like I said, to create the electrophile, to remove the halogen, including its electrons. So that's the key point, is we want to take our acyl chloride, remove the chlorine and its electrons, which forms AlCl4 minus. We're basically cutting that bond and taking the electrons with us onto the halogen carrier. Again, you can talk about the reformation of the catalyst, which actually I'm going to do at the end this time. So what happens with this mechanism then? So we've got our electrophile. It's an electrophile because it's got that positively charged carbon, not delta positive, that's a full-on positive charge, because the electron that it was sharing with chlorine has been removed from it by the halogen carrier. So that carbon is now full-on positively charged. That full-on positive charge is attracted to the area of high electron density within the benzene. And the benzene is attracted, sorry, the electrons in the ring are attracted to the positive charge on the carbon, and you get the transfer of electrons. As always, this is the slower step because we're destabilizing the ring system. That means we end up with where am I going to stick it? I'm going to stick it straight up, I think. Let's try and do that nicer. There we go. Hydrogen, and then so that's attached directly to the carbon. Remember, it's attached to the carbon. The carbon was originally delta positive anyway because it was attached to a electronegative chlorine and an electronegative oxygen. So that carbon starts off as being delta positive, and it gets a full-on positive charge when it's created, when the electrophile is created. So it's got to be attached to the carbon. And then we've got the rest of the acyl chloride there. And again, your positive charge needs to be spread across all carbons except for the carbon that's got 4 bonds, because it spreads it out around the ring system. I'm trying to make this look a little bit neater. There we go. How do we then reform the ring? What happens next? What drives the reaction? And that is the step that drives the reaction, because that's the fast step, the reformation of the reforming of the delocalized ring system, and now we have attached that group. That's really useful, this, because that group is nicely reactive. We can get it to do whatever we want, or not whatever we want, but you can get it to do lots within drug synthesis and stuff. So very, very useful. I haven't given myself much space. Whoops. How, oops, plus H plus, I need to put, how do I recreate the catalyst? I'm going to do it in a different color because I haven't given myself much space, but how do I recreate that catalyst? My halogen carrier catalyst, that is. Well, I've started with AlCl4 minus. If you take that H plus that has been created, you can come up with AlCl3, that's my catalyst recreated, and HCl. So I've recreated my catalyst hasn't been used up. Okay, what type of reaction is this? This is acylation, so that's the name of the reaction. The mechanism is electrophilic substitution. The mechanism is electrophilic substitution. The name of the reaction is Friedel-Crafts acylation. Substitution. There we go.